was one of the fundamental figures of network science, working in the general aspects of network science at Aalto University, trying to get at the most fundamental mechanisms of communities, what makes complex networks complex. He worked on a very diverse set of empirical problems, looking at success in science, looking at large-scale network phenomena that is really important for us, and for me, especially as a social scientist, to understand the social networks at a large scale. So, and because our center has very strong ties with Aalto, it's especially warm welcome for me to Santo Fortunato to talk about the community structures, a very important problem in network science. So I give the floor to you, Santo. Thank you for coming.
Thanks, Vlad. Thanks, everybody. And thanks to the organizers for bringing me here. Although actually, the invitation email was for another person. So, there was Dear X, where X was a different guy. But the other guy is here, so at least there was no harm. So I'm very pleased that at the end it worked out. So I'm talking about clustering today, what I like to call necto-clustering, of which communities is just a small part. And most specifically work that we've been doing the last couple of years about several aspects of this fundamental question. Before I forget, I would like to thank all of those who were involved in these things, especially the youngest guys, although Filippo is not so young anymore, he's assistant professor at IU. And Andrea, of course, is also kind of an established guy now. But Richard and Doug are still at Aalto, still working on these things with me. And other people, Ginesca, most of you know, and people from the University of Sydney, and so on. So I guess that you already heard something about that before this talk. So what community structure is. This is a kind of obsolete picture that I'm showing you. Very basic organization in communities or modules or clusters. I may be using these words the same meaning here. Where there is a high density of links connecting nodes of the same object, the same group, and much lower, comparatively lower density of links between them. This picture is kind of obsolete meanwhile, but I will say something about that too. But this is somehow what most people have in mind when they think about clusters or communities today. So, and thinking about real networks with clusters, communities could represent people with common interests in social networks, or scholars working on the same field, so collaborating heavily with each other, so therefore there are more links connecting them, or proteins with equal similar functions and papers on the same related topics, and therefore they cite each other more often than they cite other papers. Incidentally, we have something to say about attributes, the relationship between attributes and topology today. So, but what is the thing all about? It's about three basic questions. The first question is, where does it come from? How do the clusters emerge? The second one is how to detect it, and this is of course the one that attracted most attention. There are countless methods in this business. The third one is how to validate methods. How can you tell whether your method is a good one, is better than others, is really introducing something new into the game. I will have something to say about all three questions here, not in this order. I will say something about the genesis of community structure, which is strictly related to the concept of triadic closure, or transitivity. And I will say something about validation, which in my opinion is the single most important question of the whole thing. And most importantly about the relationship between metadata, so attributes, and topology. We're still working on that. And then, about the detection part, I'm not going to introduce a new method, because there are already millions of methods, so millions plus one wouldn't really change so much. But I'm going to say something about the importance of knowing beforehand the number of clusters. And the possibility of determining this number in an algorithm-independent way. So, somehow from, if you want, first principles. More specifically, in this case, I will show it is possible to determine a number of clusters by very peculiar properties of eigenvectors. If you know random matrix theory, you can perturb a matrix and then you see how the eigenvectors rotate. But that would be the final part of the talk. So let's talk about generation of clusters, which for some reasons has not really received much attention. There are, of course, some papers discussing this. most papers introduce ad hoc mechanisms to justify the emergence of clusters, or communities. But interestingly enough, there were already mechanisms which were proposed for other purposes that actually do the job already, which is good, it's a very parsimonious model that gives you also clustering or community structure for free. The concept of clustering or community attack or community structure has been always related to, very strongly put in connection to the concept of triadic closure. So there are many testimonies of this. Mark Newman actually somehow thought that clustering emerges because, especially in the context of social networks, because there are groups. So the fact that we have often common friends, that my friends are often friends with each other, much more likely than any two persons in society, is a consequence of the fact that people tend to form groups. So this would be one way to go. Here we're going the other way. We're showing that if there is triadic closure, which essentially means, for instance, if this is a social network, there is a guy joining the group, and then he gets friends to a guy, and this guy introduces him to two friends of his, and then they become friends with a new guy. So there have been, of course, from the very beginning of networks and modern network science, 2003 in fact, models to try to explain the unusually high number of triads that you find in especially social networks. So this is a model proposed originally by Vasquez, has been refined in many ways and complicated. Also Peter Holmes here proposed right after that another one based on preferential attachment. This is not explicitly on preferential attachment, but implicitly. It consists on, it's a growth model, which means that every time you add a new node, and then of course brings some links and sets new connections with the other nodes of the system. So this is I, join the system, setting a link with any guy at random, that would be J, and then with the probability P, it sets a connection to a friend of J, a neighbor of J, and with the complementary probability 1 minus P sets a friend, sets a connection with a random guy again. And if there are multiple links, then it keeps working this way. So again, it is probabilities. So the possibility of linking to neighbors of randomly selected guys implicitly induces preferential attachment to the game, so it gives rise to a broad distribution of connection. This is fine. At the same time, of course, you are, especially if P is not so low, you are closing many triangles in the process, so you also get a high clustering coefficient for the system. That was the reason why the model was introduced. It's also a model that can be discussed analytically, it's a nice one. What we did recently was to show that this model naturally gives rise to clusters as well. And the picture is the following. So you start from some number of nodes at the beginning, then the system grows as I told you, there are new nodes joining the system. And because of random fluctuation, at some point there will be some parts of the system which are slightly more dense in links than others. It's just, it just happens because of fluctuations on a sparse system. Because of that, the process of triadic closure will be happening with higher probability within those denser areas, which then become even denser, until at some point they become sufficiently big that they will specialize themselves by giving rise to denser parts and less dense parts, which will then separate and give rise to different communities. So this is what happens here. So this part becomes denser, and the other part as well, and then there are two models created, and so on. Of course, the system gets bigger and bigger, and then these clusters fragment because they become bigger, and then they become more inhomogeneous, and because of this inhomogeneity, then there will be higher density of triads inside, and they will give rise to multiple clusters. So this is the heuristics, how to show this quantitatively, because it's always nice to show pictures, but what to make sense of what we see. One way to do it is to measure the so-called embeddedness of the clusters. Embeddedness, very naively, can be quantified by computing for a cluster the internal number of neighbors of the cluster nodes. So how many nodes of a cluster are neighbors of any node of the cluster, divided by the total number of neighbors of the clusters, of the nodes of the cluster, so including also the ones which lay outside. The idea is that if this number is close to 1, it means basically that most of the neighbors of the nodes clusters are the cluster's nodes are internal. So there are very few bridges to the rest of the system. So, in fact, we are using a slightly more refined measure because, even this way you can still get fairly high values also for random graphs. So this is actually what this is, what you can see here. So this would be the external nodes. So those would be the external neighbors, and all the green ones would be the nodes of the clusters and then also internal neighbors. So here you see this quantity, not exactly this one, but a similar one, which somehow discounts for random fluctuations for two different versions of the model obtained for two different values of p, the two extreme values. P equal to 0, this means that there is no triadic closure, and p equal to 1, which means there is only triadic closure. So there is a very, very high probability, basically, always probability, always closing the triangle in the process. So p equal to 1 corresponds to the blue curve, and p equal to 0 corresponds to the green curve. Here, as you see, of course, the values are very different, and the embeddedness is very, very high for the case in which you have only triadic closure. This is a zoom in of this part of the curve here. N is the number of nodes that you add into the system, so it's a notion of time. So the system gets bigger and bigger. As you see, after a while, the embeddedness stabilizes to some sort of flat value, fixed value. What I wanted to show you here is that these arrows, when there is a sudden drop of the embeddedness, is because two classes have split. So classes, of course, are found with some community detection method. We found them with InfoMap. We use also other methods, and the picture is entirely consistent. So this happens because when you separate two clusters, when the clusters are considered different by a method, then, of course, the numerator here will suddenly decrease, whereas the denominator is pretty much the same. So there is a sudden drop of that. So all these things indicate that a cluster is split in two parts in the process. And finally, if you want to know the details, because we also analyze other models generating triangles. So this is just the simplest one of them, the one also which is susceptible to analytical treatments, but there are, of course, other versions. You can also read the paper published last year, 2 years ago. Okay, second question, validation. How to test clustering algorithm. There are two ways to do it. There is no other way to do it, in fact. One way is that you invent some networks that you believe they have clusters, some concept of clusters, and then, of course, you expect your system, your method to detect those structures. So this would be the first part of this. The class of artificial networks which were used for that are generated by a broad family of networks known as stochastic block models, which have the following ingredients. There are Q blocks, so groups of nodes, so each node receives one of Q colors, and the probability that nodes are connected depends only on their membership. So the probability that the node I of group R is attached to node J of group S is just a function of R and S. So it doesn't really depend on which specific node you're picking with that color. That's the most general notion. So this matrix, ERS, gives you then these probabilities. So it's then a Q times Q matrix, because Q is the number of blocks. And here you can see some sort of schematic example of this matrix where the blocks indicate the value of the entries of the matrix. The bigger ones correspond to larger values, smaller ones correspond basically to 0. So you see you can have different types of scenarios. You can have larger probabilities here on the diagonals, meaning that then there is a high probability for nodes of the same color to be linked. That would be the scenario of communities, but there are also other scenarios. You can have co-periphery structure. You can have anti-communities, in which basically it's just the opposite scenario, in which you have many links between the groups and very few links inside the groups. You can have everything this way, as long as you have blocks, and the probability just depends on the blocks. This is basically just a schematic picture of one of these models you can construct this way. In calculations, in the literature, there is a special version of this model that is being used. It's called the planted partition model, in which basically what you do, you just set to P in the diagonal elements of the stochastic block model matrix, no matter what I is for any value of R. So So there is the same probability for nodes of the same color to be linked, regardless of the block on the specific color. And there is a common probability P out for nodes of different colors to be linked. So there are only basically two variables, just to keep things simple. Blocks have identical sides, we call it n, small n, and so the Q times n gives you large n, which is the size of the system. I just introduced also these auxiliary variables because you may see them in some of the plots. This is the expected internal degree of the blocks. So if there is a probability P for each node to get a connection, to make a connection with nodes of the same color, then there is an expected number P in times n minus 1 of neighbors for the nodes of a given color. Where mu out is not the total external degree, but is the external degree with respect to any other block. Because that's what you really need to compare. And the idea behind this is that if the probability P in is bigger than P out, the groups are communities, because there is a higher density of links inside the blocks than between the blocks. So that would basically mean mu in bigger than mu out. Some years ago, we have introduced a modification of this model to include some realistic features of networks with communities, because the previous model had all identical block size, so the clusters are the same size, and the nodes have actually the same degree. Distribution is peaked, which is of course not what we really see in real networks. So we introduced what is now called the LFR model, of which you see here a snapshot, which is a model just like the previous one, but which has a parallel distribution of degrees and a parallel distribution of community size. As you see here, the blocks now are heterogeneous, there are small groups, there are bigger groups, and although this is more difficult to notice, some of the nodes have larger degree, much larger degree than others. So it was some years ago, and here is where you can find the code to produce these networks. It is being used, luckily, quite often lately. It's one of the standards of the field now. And that we use right away to test the performance of a number of popular methods right after we introduced this benchmark in 2009. This is the library that we used, getting methods from different sources directly from the authors. Sometimes they were coded by ourselves, sometimes they were public accessible. Methods of different kinds, method based on hierarchical divisive strategies like this one, famous Given-Newman method, methods based on modularity optimization, the modularity by Newman and Girvan, method based on random walks, so diffusion, and so on. But I wanted to show, just to give you a flavor of how things work in this way. The mixing parameter mu-t is pretty much the same thing as the embeddedness that you've seen before. In fact, it's 1 minus the embeddedness. So mu-t tells you basically what is the fraction of external links that the node has in its community with respect to the total number of links or neighbors that it has. So if it's 0, it means that all its neighbors are inside this group. If it's close to 1, it means that all its neighbors are outside the group. So of course, the community-like scenario is more believable if mu-t is close to 0. In that case, you expect that most algorithms can do a good job. And here you see the performance curves for the 12 methods that you see, one corresponding to one of the plots here. Different curves correspond to different versions of the benchmarks, different size, different distributions of cluster sizes, just to see how sensitive the performance is on these variables. And so here you have mu-t, so you see performance which is measured by the similarity between the detected and the planted partition is normalized mutual information, is the variable, but of course you can choose other variables. To measure that is 1 when the two partitions are identical, and starts to become close to 0 when there is basically a random correspondence between the two partitions. So you see, of course, the performance degrades, and then you see that the best message is the one that somehow decays the farthest with respect to the others. So this is what people have done. I take the chance also to mention briefly something that, in my opinion, everybody should do whenever a new method is introduced, or testing of other methods is done, which is the so-called negative test. I mean, if you have a random graph, so of any kind, in which basically there is then the same probability for nodes to choose each other, compatibly with some constraints like the degree of the nodes, possibly, then you don't expect to have clusters there, because there are no, there is no block structure. So the nodes can choose each other arbitrarily. So in this case, you do not expect to find clusters in there. So if you find clusters, there is something wrong with your algorithm. So what we did here, we took two different random graphs, scale-free graphs, Barbasi-Albert and Erdős-Renyi graphs. These are all networks with 1,000 nodes. And then we checked how many clusters were found by the methods as a function of the average degree of the networks. So low average degree means sparse graph, larger average degree means graph that starts to be a bit more dense. And you see that especially when the network is sparse, also very well-known method, Infomap, Louvain, also are fooled and they find small groups of nodes. So it would be good to have a way, whenever you introduce a method, to identify this as bad results somehow, and as known results, false positives. Because if you don't have it, then whenever you find a cluster, you don't know. If you also find clusters in random graphs, you don't know whether your network, the one that you're studying for your own applications and interest, has really a community structure or not, anything meaningful. So this is somehow a parenthesis. Next thing is metadata. So the other thing is how to test methods. I mean, the problem with artificial network models with clusters is that, of course, you are selling some specific idea what the cluster is. So if you stick to one of these ideas, for instance, to our model, or to generate a stochastic block model, the best method is the one which gives the best performance on that one. Which, of course, makes sense. It's desirable, I mean, to the extent that, of course, there are a number of attributes of these models that people would like to have, and they expect to have in real networks with clusters. But, of course, these are always simplified methods, simplified models. So they also neglect a number of realistic features. So to stick too much to artificial models, of course, is also risky. Can also take a bit off course. The other thing that people have done, at the same time, not an alternative to that, is to see if it's possible to detect the partition of real networks in which some attributes, some metadata information was available, in which then the colors are given by an external source. I don't know, the major of students in the university, or the function of proteins, or other things, or some specific interest, books that people are interested together. The problem is that until recently, there were not many examples of networks like this, in which there is some sort of group membership which is independent of the topology, which somehow comes from different inputs. Recently, fortunately, instead, starting from Url we put together quite a big collection of networks, although I must say they're all almost identical. Most of them are mostly social networks, very similar ones. But there are many, they are different sizes, some of them are millions of nodes. And for many of these millions of nodes, it's possible to have information about groups, group memberships, like groups of users in LiveJournal, for instance. We also augmented this collection. We also introduced other networks in that, deriving the attributes from other sources. So we put together some, quite a big library, which of course we are free to share one day, we'll publish it. But it's essentially, the Stanford collection plus others. A few other examples, also from biology that we put. And the idea is then, of course, if the methods, which are basically topological methods, they're based only on the graph structure, are able to identify these metadata groups. I mean, you may feel that there is no need to test that because people are taking this assumption for granted. They say, okay, yes, so there are the attributes, and of course, for instance, like in this case, it's a famous, infamous Zachary Karate Club. You know the history, there are these guys, members of the club, the United States. Then there was a fight between the instructor and the administrator, and the president of the club, and then they split. So this will be 1 and 34. The friends of the president went to the president, the friends of the administrator went to the administrator, and they formed two different groups. And the idea is that will any of this method be able to separate these two things, to distinguish them, the circles from the red circles from the blue circles. I would say, this network has created a lot of damage to the field, in my opinion, because it's convinced people that a lot of crappy methods were actually working. So now we know, so we wasted some 10 years for that. I know that there is even an award, for this. The first guy to mention this, not at this conference, and not in the conference. So I wouldn't give this award just because of what I said. I think that it really. So forget about this. It's a very small one. It's not so difficult if you tune things to reproduce the clusters. Doesn't mean that your method is any good, because many methods that do very well on this one also fail miserably in other cases, larger networks, more complicated structures. But it's just an example. So we're looking for systems like this in which we have then some sort of information about the nodes, the group membership, and then we want to see if it's possible to retrieve it with our methods. So what we did recently, we took then our collection, which is, like I said, strongly overlapping with the Stanford collection. You can see some of the examples here. So this is the karate club, so it's included there, football. These are classic benchmarks, that's also very small. Political books with 2 different orientations. Political blogs also that link to each other. And this is actually something that we invented, this Debian software package dependencies network. And then there is the internet, then there are a number of social networks. Also very big, as you can see. So some of this is also difficult to run some of the algorithms because they are really big. So you see the number of edges, you see how many communities are there based on the attributes. There are the 2 of the Zachary that you've seen before. And then, of course, many others, up to millions. In some cases, of course, there was no information about the attributes. And what we did, basically, we took a big collection of methods that you see here, from different sources, so from different principles, modularity optimization, label propagation, click percolation. Our own method is also there, so we didn't want to be out of this context. And the columns here indicate basically what is the similarity between what the methods find and what these metadata groups represent. So you see for the small benchmarks like karate and so on, you get quite high values of the similarity. It's not the same for all methods, and methods are also bad at that one. But you can see that there is a difference. This is the LFR benchmark, the artificial benchmark we introduced before. But for the newer, larger networks, especially the social networks, you see that the performance degrades. So that there is some sort of disconnect between these 2 things. So, I don't want to draw sharp conclusions out of this, also because you can always say this is a specific set of data sets, right, of data. I just want to warn people, when they use metadata to validate methods, that maybe they shouldn't expect too much from this, and it's not necessarily their fault or their method's fault. It's because metadata sometimes are not really related to topology. What we found, in fact, we are continuing on this now using a stochastic block model, something that should be appearing in the next weeks, that in some cases metadata help to identify the groups, so there is really a positive correlation with topology. In some cases there is no correlation, in some cases there is an anti-correlation. The groups with the attributes are really distinct from the ones that you can find in any stochastic block model kind of setup. So there are caveats about using artificial benchmarks, but there are also caveats in using metadata. You don't have to expect always, so you shouldn't be also frustrated if your method doesn't reproduce the groups of friends in live journal. Because nobody could. And at the same time, it's also an indication that maybe topological only methods are not sufficient to extract what we want to get from the data. So we should perhaps try to combine, and some people have done this lately, and we are doing this too, combine topology with metadata to do a better job. On the other hand, if you have information about your system, why shouldn't you use it, right? But the more the better. Okay, so the last thing I want to say now is something about the detection. And it's again topological only. So it's not really a method that I'm going to propose. I have to say there are too many methods and they don't work. So why introducing another not working method? But in general about the issue that there are a number of whole classes of methods that really require the number of clusters as an input before even starting to operate. Stochastic block model is actually block models are because they are used to produce benchmarks, but they're also used to make the inference of the groups. So through Bayesian inference, maximum likelihood, as you know. So they're also methods themselves. So in this case, you need to tell them how many groups there are. But also in many data clusters, you usually have to tell how many groups you have. Optimization, which also predicts how many classes there are. But not only that, label propagation. Most of the methods that were in the list before do not need this input. They try to extract this information from the data. So we show that if we give instead the right number of clusters as an input, so if you constrain, say, the maximization of your objective function for those methods which are based on optimization, if you constrain this optimization only among those partitions with that fixed number of clusters, that performance improves considerably. Also dramatically, even going over structural and systematic biases of the methods. Most striking example is here modularity maximization. So you see this is mu out. Tells you what is, how many links there are outside of the cluster. For a fixed mu in, at some point, of course, mu out will become bigger than mu in, so there will be no detection possible. So you expect very big, poor performance. And for modularity here, which would be the orange curve, and modularity with the knowledge of the number of clusters, so constraining the optimization only among those partitions with the correct number of clusters, you see that the performance is really much better in that case. But then, we're just shifting our attention from one problem to the other one. How do I know how to determine the number of clusters? So, just the same. Is it sure that it's much easier to do that? Can we really do that? Recently, there's been a couple of interesting papers by a group of Zeborova et al. And also Matt Newman that have proposed interesting ways to extract this number of clusters in sort of principal way by checking the distribution of eigenvalues of specific graph matrices. The non-backtracking matrix and the flow matrix. Flow matrix was introduced by Newman, correcting for the degree. Heterogeneity, and the non-backtracking matrix was proposed by the group of parents. But eigenvalues, of course, is also, counter-indications. They can also be strongly focused on specific, they can also correspond more to degree than to clusters. Besides, at the end, for the detection, you always need the eigenvectors. So what we did for the first time, we tried to extract the number of clusters from the eigenvectors by doing something interesting, also new to me, because I didn't know anything, or not very much about random matrix theory before. So what you can do, you can perturb your adjacency matrix. So you take the adjacency matrix, which I remind, especially to the youngest here, it's the matrix which has 0 entries if there is no links between the corresponding nodes, pair of nodes, and there is 1 instead if the two nodes are connected. So you take the adjacency matrix of your network and you perturb it. You do what is called a Bernoulli perturbation, which means there is a matrix E, which is a random matrix. Half of the elements of E are +1, the other half is -1. They're distributed randomly. And you add it to the adjacency matrix after multiplying it by a small parameter epsilon. So then you focus on this new matrix. Epsilon is small, can be arbitrarily small, but of course, to make the calculation, you should be at least bigger than your precision. So, and what we do, we compute the eigenvectors of this modified matrix, and we compare them with the eigenvectors of the original adjacency matrix, where the first eigenvector is the one with the largest eigenvalue, and the second with the second largest eigenvalue, and so on. So there are a number of theorems about these spectral properties of perturbed matrices. There are well-known bounds. Davis, Kahn, and Wedlin, for instance, have proved a theorem which sets a lower bound on the angle of rotation of the leading eigenvector after perturbations like this, which depends on epsilon, of course. And recently we managed to extend this result also to more eigenvectors. But I don't want to get into the details of this because it's really technical, and even to me. I want to just get to the main result, which is the following. It turns out that after you do this perturbation, there are 3 peculiar behaviors. The leading eigenvector has the smallest rotation angle. It's the one that changes the least from its original vector. Then there is what is called the community eigenspace. there are q minus 1 eigenvectors, which are from the second to the qth, if you go down in the progression of the eigenvalues, which rotate together. I mean, not so slightly as the leading eigenvector, but not too much. Although it really depends on the specific system. I'll tell you what it means in this example here. And the remaining eigenvectors, they all rotate together. It's called the bulk eigenspace, and they basically rotate instantly by 90 degrees. So like this, even if epsilon is very small. The one thing that was puzzling also to me is that how is it possible if epsilon is very, very small that you can get these things? But this is the difference. Spectral analysis is a very, very complicated thing. It's not continuous. There are examples I can give you in which introducing the slightest perturbation you get a rotation, sudden rotation of things. The nice thing here is that not all eigenvectors rotate the same way. Some of them rotate faster, some of them rotate less. And because of that, you can identify groups of eigenvectors behaving the same way. Especially this community eigenspace. So let me show you this with this picture here. So this is a stochastic block model. So it's a system that we know that it has blocks. The blocks are 16, 10,000 nodes, so it's not so small. And we take here the first 100 eigenvectors. So on the x-axis you have the index of these eigenvectors. So this is the leading eigenvector, and then the second, the third, and so on, all the way to the hundredth largest eigenvalue. And the symbols here represent the angle of rotation of the eigenvector of the perturbed matrix with respect to the eigenvector of the original matrix. The leading eigenvector you see doesn't rotate very much. It's given by this plus here. Then there is a community eigenspace. These are in fact all eigenvectors from the second to the 16th. And then there is, you see, a separation with the bulk eigenvector, which rotates by almost 90 degrees. These are degrees. I mean, angle degrees, not radians. So this is how you can identify the number of clusters. Of course, it's not always so easy. This is a case in which blocks are clearly identifiable. So they are very dense somehow with respect to the external connection. And another nice thing that we found, that for which we do not really have an explanation, is that these eigenvectors rotate in pairs. Like the second has this most similar angle of rotation with the 16th, the third with the 15th, the fourth with the 14th. So they are in symmetric pairs with respect to the center of that group of eigenvectors. And the same goes for the bulk eigenvector, although that is more difficult to see because most of the angles are close to 90 degrees. Yeah? It's over? Okay, I'm sorry. Yeah. Okay, so, all right, so the last thing I wanted to show is that if you take the stochastic block models again, for instance, for 8 clusters and 16 clusters, and you check the difference in the rotation, in the angle of rotation between, for instance, in this case, there are 8 clusters, so you take the first eigenvector of the bulk, which is number 9, and you make the difference of these angles, you see that the two groups of eigenvectors converge at the so-called detectability limit, which is the limit in the mu out, in this case, so in the density of, in the probability of linking, oops, oh, that's really sharp. No, sure. It was the last, was the last, anyway. So 3 things then. Even if you don't see them, let me see if I can recover from them. So about the genesis of triadic closure and clustering are very strongly related. So we show basically that any model that introduces a high probability of triadic closure generates classes as well. The second thing is that, if you want to use attributes, so metadata, to validate methods, you should be careful because they're not necessarily related to what most of these methods usually are after. And the third thing is that, if you want to find the number of classes in an algorithm-dependent way, then you can use these peculiar properties of rotational eigenvectors after perturbing the adjacency matrix. And that would be all. Okay, thanks.
Thank you very much. Thank you very much. Now, the parallel sessions are starting, so I would like to suggest that we move our questions out with coffee. and keep your questions, and let's make this a group discussion. And I would like to give this a token of appreciation to Santo for this very interesting survey of looking at cohesion metrics and how to diagnose them. So once again, I would like to ask you to move together to the coffee break, and